When you look at something like this, do you ever think, wow, it looks so beautiful. I wonder if I can reduce such complex diagrams to simple math equations? Well, if you did, you're in for a ride, because I'll show you exactly how you can model this with just a few variables. But first, let me tell you what this is. This right here is a hypocycloid. And so is this, and so are all of these. If we have any two circles where one is lying and rolling on the interior just like this, and we trace a point on a smaller circle, for example, we have this red point here, as a smaller circle rolls around, we get a hypocycloid. Now, what if I tell you we can make a general equation for all of these distinct figures, just like how we can make a general equation for any line with y equals mx plus b, to map out exactly how this red point moves as a smaller circle rolls around. It might seem difficult, but it's actually pretty simple. With this general equation, let's first observe the movement of two circles, one of bigger radius r and one of smaller radius smaller. The smaller circle is moving in this clockwise direction, shown by the arrow. And after some time, let's say the circle moves and rotates as such and ends up at this configuration. Okay, now we can analyze this movement to create a general equation. So this was the starting position, and after some movement, this was the final configuration. And also, I labeled the center of the bigger circle as C and the center of the smaller circle as J. Okay, to reiterate our goal, we need to figure out the general coordinates of P as it moves around the curve relative to its center, C. Let's look at a circle, for example, to understand how this works. Okay, we know that the equation of a circle is equal to x squared plus y squared equals r squared. But why? For any circle, it has a center. For here, let's say the center was 0, 0. And any point on the circle will be a distance exactly r away from the center. And if we draw a triangle to the point P, we can see that the coordinates of P have to always satisfy the general equation x squared plus y squared equals r squared, formed from the usage of the Pythagoras theorem. Using trigonometric ratios, we can also express x component and y component in terms of the angle of rotation of P around the center as, for example, let's say that's z radians and just the radius r. As you can see here, using trigonometric ratios, we're able to express x as r cosine z and r sine z using trigonometric ratios. To make more sense of this, let's go here. Let's say we have a point r0, and it rotates an angle of z radians around the center. Okay. So again, we have the x component as r cosine z and y component r sine z, and the coordinates of P can be expressed as r cosine z and r sine z. Now the equation of the circle can be formed as r squared cosine squared z plus r squared sine squared z equals r squared, where x will equal to r cosine z and y will equal to r sine z. Now, using what we learned here, let's try to make a general equation of the hypocycloid. Okay, so how might we show the coordinates of P relative to the center C? So we label the center C as 0, 0, as we did to get the general equation of the circle if it was at the origin. So we made C 0, 0. Okay, first of all, it might be a bit difficult to get the coordinates of P instantly from C, because P is rotating around J and then the circle of the center J is rotating around the circle center C. It might be a bit difficult to jump from C to P directly. But what if we actually get the coordinates of the center of the smaller circle J relative to C, and then we get the coordinates of point P relative to J, and then we add the x components and y components up? Okay, that might sound a bit confusing, but you'll understand once we start doing it. Okay, so let me just write down what we're doing exactly. We're going from C to J, right? Figuring out the coordinates of J relative to C. And then we're going from J to P, where the coordinates of P relative to J, and we'll add the x components and y components up. Okay, first let's figure out the coordinates of J relative to C. Okay, so our first order of business is figuring out the coordinates of J relative to C. So we have the C 0, 0. Okay, so first let's look at the motion of J. As a smaller circle rolls around the interior of the bigger circle, J actually moves in a counterclockwise direction like this. Now you might be thinking, J, this actually represents a circle, a circular motion. Basically, what's happening is that J is moving in a circular motion around C, and that's exactly what we have done here. We drew a circle to represent the motion of J around C as it moves around like this. Now, the radius of this is just big R minus R. Why? Because the distance from here to here is R, big R, and the distance from here to here is small r. So the radius of this is big R minus small r. So let's say in our example, in our movement, let's say the point G, after the rolling was finished from here to here, right? After the rolling was finished, let's say J rotated an angle of theta. So as the small circle got to this point, as settled around at this point, as we've seen here, it rotated an angle of theta. So that's what we have here. It rotated an angle of theta, and we've represented that here. Now remember, in the circle example, we can represent the coordinates of G, general coordinates of G, in terms of the rotation of J around C. And that's exactly what we've done here. The coordinates of J relative to C is just R minus R, which is the radius of the circle, and cosine theta. Theta is the angle of rotation of J around C. And that's what we've done for the y as well. So now we've successfully got the coordinates of J relative to C. Let's do the same for P. All right. Now let's try to express the coordinates of P relative to J. So in the starting position, P was here, and in the ending position, after the small circle basically finished rotating, P was here. So basically, relative to J, P moved from this position here all the way to this position. Let's say that was represented by alpha. So let's say this was alpha. Now we have established before that the general coordinates of P can be established with just the radius and the angle of rotation of P around J. Because the angle of rotation of P around J is alpha, right? You might be quick to say that the x coordinates and y coordinates of P relative to J are r cosine alpha and r sine alpha. But that's actually incorrect, because when we say something like cosine alpha and sine alpha, and we have that alpha is actually positive, is positive value, right? We're saying it rotated like 5 radians around J. What's happening is that we're actually going in this direction. Because alpha is positive, when we say cosine alpha or sine alpha, the angles or the values represented by cosine alpha and sine alpha are represented by the coordinate of moving a point from this direction, from this point to here, by an angle of alpha. So after you move an angle of alpha, you end up here. So let's say this point was P. You end up here instead of ending up here. Again, alpha is positive. We move in the counterclockwise direction, we end up here. But P is here. P is in the second quadrant. And how do we account for this? All we have to do is just multiply the y coordinates by a negative sign to put it back into place. To put this y coordinate back into place like it's supposed to be and make it correct. The x values are still the same because moving here or not, because it's symmetric around the x-axis, the p coordinates will still hold the same x value. So we don't have to do anything to the x value, the x coordinate of p. All we have to change is the y coordinate of p and multiply by negative sign. So now we have the coordinates of p relative to j. Okay, now we can actually go to the final step. We can now represent p relative to c. How will we do this? We just simply add the exponents up. This expression showcases the coordinates of j relative to c. After we get to this point, we just add the other x values. This x value represents the coordinates of p relative to j. We move from here to here and then here to here by adding up the vectors. The same goes for the y coordinates. However, we still have a problem. Our general equation for the coordinates of p as it translates around c is not fully simplified yet. We can reduce it, but to do this, we must understand exactly what's happening as a smaller circle rotates around the bigger circle. Okay, first you have to realize this. You have to realize these are parallel to each other. So we established before that this was theta, We know that J rotated theta radians around C. So we know that this is also theta. Okay, let's look at it. When a smaller circle gets to this position from the initial position, right, when the smaller circle rolls around like this, P, which was actually like here, so it would actually be touching, it ended up here. Now you have to understand that the distance covered when the circle was rolling around, the smaller circle was rolling around in the interior, it's the same as this arc. This arc represents the distance covered as P rotates around the smaller circle as the smaller circle rolls around the interior of the bigger circle. Now this distance covered just represents how far it traveled around the bigger circle, which basically means that this distance and this distance are the exact same. Now, as they're the same, we can equate the lengths to each other. So let's do exactly that. So basically, the length of an arc is represented by the angle that subtends the arc and the radius. So this, right, the bigger, like the arc represented by a bigger circle, will just be r and then theta, right? And this will be equal to this arc length plus this arc length. Now we know that the angle represented by here is alpha. So we have r alpha plus actually theta as well. Theta. Now we have theta because this is parallel to this. So this is actually also theta. And as we know that this is the complete arc, we have alpha plus theta. So r multiplied by alpha plus theta represents the radiance or the coverage of P as it rolls around, as it basically translates around the smaller circle, as the circle rolls around the bigger circle. And we have this. And now simplifying this, we actually have alpha is equal to r minus r divided by r minus theta. Okay, now we have r minus r multiplied by theta. So we have an even simplified version now, and we can now represent our general coordinates as such. So instead of this, we can write it as r cosine r minus r by r times theta. The same goes for y coordinates. Okay, so if you have successfully created a general equation that can express any hypocycloid that we want based on the parameters of big R, small r, and theta, the angle represented by the translation of the smaller circle around the bigger circle, or basically the angle of rotation of J around C. So in the next video, I'll talk about specific hypocycloids, and by changing the parameters and also the ratios of R, the big R and small r, we can make a lot of really cool looking hypocycloids just like we want. I think you saw two of them at the start of the video, and I'll explain how they work as well. All right, thank you so much.